All right, here we are in 9.7. What we'll do in this section, and I'll hop right into it, is extend what we did with inscribed and central angles. That is the sort of conclusions that we drew when we described the relationship of an inscribed angle to the arc that it cuts and a central angle to the arc that it cuts. So you recall that we said about central angles, as you see on the left, angle BCA, where the vertex is the center of the circle. We said that in this case, the measure of the angle is equal to the measure of the arc that it cuts. And this was like a decree that we made. This was how we defined arc measure. We said that by definition, it's the same as the central angle that cuts it. And then we proved, in a three-part proof, that the measure of an inscribed angle is precisely half of the arc that it cuts. Now, there are other possibilities here about how it is that an angle can be related to a circle. And I do mean to discuss only angles, both of whose sides interact with the circle in some way, that is, intersect the circle in some way. If one or both of the sides didn't intersect the circle, then of course we could draw no conclusion about the relationship of an arc cut to the measure of the angle. So only angles that intersect the circle, both sides. But there are other possibilities than central and inscribed angles. And to get at those possibilities, we need a new definition, the definition of a secant. And a secant is a kind of extension of the definition of a chord. A secant is simply a line, a ray, or a segment that intersects a circle twice. So a chord does, of course, does count as a secant because its endpoints lie on the circle. But there are other objects that also count as secants, like the line, for instance, N that you see pictured in the diagram. Now, here's one possibility about how it is that we might have an angle that whose two sides intersect a circle, its relationship to that circle. Um, this is where two secants meet inside of the circle, like in the diagram in front of you. We have the secant CD and AB that intersect at the point E, and obviously angles are created, four of them about E, situated inside of the circle. And what we want is the relationship between a measure of one of these angles and the arc that it cuts. Actually, it's a little bit more complex than that. We will consider the measure of angle AEC. What we will find is this, is that it is half of the measure of the arc it cuts, which is AC, plus the arc that is cut by its, I sometimes call it its vertical twin. Because again, we had two secants that intersected, which gave us a pair of vertical angles, AEC and BED, another pair as well, but that's the one that I wish to focus on. And the measure of one of those, like AEC or BED, because they're equal, is half of the sum of the two arcs marked. Now, as for how it is that this actually would be proven, well, what we need are inscribed angles. And this proof, I won't do all the proofs in this section with you, and the proof that I'm about to give will really give the flavor of what it is that we have to do. Now, what we do is we add a construction. So construct CB. And then I'm going to label some angles for you. And note that angle 1 is exterior to triangle BCE, and that 2 and 3 are its remotes. And we have a theorem that applies in this case. If you don't recall, it's the triangle exterior angle equality by the TEAE. It follows that angle 1 is angle 2 plus angle 3. But now note, okay, so that fact had to do only with the triangle that was present, nothing to do with the circle. But of course, the circle will have a role to play, and the role that it has to play is this: is that angles 2 and 3 are angles inscribed into that circle. But angles 1 and 2 are inscribed. Thus, each is half of the arc that it cuts, which we of course can find by inspection. Thus, by the inscribed angle theorem, angle 2 is, oops, I said angles 1 and 2. I should have said angles 2 and 3. So let me make that correction. So it should be angles 2 and 3. Sorry about that. Those are the inscribed angles. So angle 2 is, follow its sides out, you'll find that they terminate on the circle at B and D. So the arc cut is arc BD. And likewise, angle 3, half, of course, inscribed angle theorem, is half of the arc that it cuts, which is arc AC. So what we now have is that angle 1, which of course is our angle AEC, that was just a relabel, that is equal to half AC plus half BD, the arcs. And then at this point, we simply factor out the 1/2, and then we get half of the sum AC plus BD. And with that, the proof is complete. So that's very much the flavor of the proofs of this section. Notice that there were two crucial theorems involved. One of the theorems was the triangle exterior angle equality, and the other was the inscribed angle theorem. Now, here's another possibility as well, and I will not go through and give detailed proofs of these. I'll simply discuss what they say and perhaps say a little bit about how it is that one would prove it. Okay, so another possibility is this, is that we have an angle whose two sides are secants, and the vertex of the angle lies outside the circle. Okay, so in the previous proof, we had two secants that intersected, and then the angle with which we were concerned, its vertex was inside the circle. So now in this case, the vertex is outside the circle. So we have angle BAC formed by two secants. And then what follows in this case, there's a curious dissimilarity between this result and the previous result. There is a certain similarity here. That is, we have to talk about two arcs that are cut, but in this case, we have to talk about their difference. Okay, so as you follow out the sides of angle A, you'll see that it first of all cuts arc DE, and then it cuts arc BC. And the measure of angle A is half the difference of those. Larger minus smaller, because of course we don't want a negative for angle A. So subtract those arcs, BC minus DE, take half of that difference. That is the measure of angle A. Now, as for how this gets proven, well, I do believe that one constructs CD or BE, and then one considers angles as before, angles 1 and 2 and 3, and by the triangle exterior angle equality, 1 is 2 plus 3. And then notice then that what we want to do in this case is solve for angle 3. So what that will mean is this. Well, 1 was 2 plus 3, so that will mean that 3 is 1 minus 2. 3 is 1 minus 2 just by simple algebra. Excuse me. And notice that angles 1 and 2 are, as before, inscribed angles, which means that each is half the arc that it cuts, and the proof proceeds in very much the same kind of way. So here's a third possibility. In this case, we have a secant and a tangent that meet, and they meet at the point of tangent C. So look at our angle ABC. One side is a secant, that is AB. The other side is a tangent, that is BC, and B is the point of tangent C. And once again, the result is this, is that the measure of angle ABC is half the measure of the arc that it cuts. So it's very much like the inscribed angle theorem, but notice that this is not an inscribed angle because one of the sides is not a chord. So our proof of the inscribed angle theorem doesn't apply. And you will prove that on the worksheet. And once again, what one should expect to do is to have triangles and have exterior angles and so on. And then the final possibility is this, is where we have a secant and a tangent that meet outside the circle. So in this case, AD is the tangent, AC is the secant. They meet outside the circle to form angle A. And what we will do is we will prove that, or what you will do on the worksheet is prove that angle A is half the measure of the two arcs that are inside of it. One of those is CD, there we go, and the other is DB. So subtract those two, take half, and that's the measure of angle A. Oh, sorry, I said that was the final one, but it's not. Obviously, there is one more possibility. And the final possibility is that you have two tangents that meet outside the circle. And once again, we have two arcs that are cut, two arcs that are in the interior of this angle. In this case, they are BDC. That's the larger, and BC, the smaller. Remember, if we use 3 letters for an arc, that means we have a major arc. So BDC is what appears to be the major arc in this case, and BC is the remainder of the circle. And the measure of angle A is half the difference. And how does one do this? Well, one does this with construction of a segment that gives a triangle, and one has an exterior angle, and so on. So one attempts to employ the same sort of technique that we saw before.